All right. So as I was saying, supernova create all the heavy elements beyond iron. All right. So all right. As I said before, most stars end up as white dwarfs. However, when supernova go off, you have a star that is usually at least 10 times the mass of the sun or greater. And those, of course, because there's an explosion, you lose tremendous amount of mass into space. But if what remains is between 1.4 and 3 times the mass of the sun, so this is after the supernova explosion, what happens is that star turns into what's called a neutron star or a pulsar. The ones that we can detect are called pulsars. And these are rapidly rotating neutron stars, and these are extremely dense objects. Beyond 3 times the mass of the sun, it turns out that nothing can hold up. The neutrons are what holds up this star. It's an extremely tiny object. The white dwarfs, basically, the ones beyond, that are less massive than 1.4 times the mass of the sun, are held up, and there's this quantum mechanical effect that holds them up, that has to do with their electrons. And those objects can be, they're roughly, you have something 1.4 times the mass of the sun or less that is around the size of the Earth. It collapses down to about the size of the Earth. Those are white dwarfs. Neutron stars, you're collapsing an object down to about the size of a city, so maybe 10, 20 miles across. This is the most dense object there is. And then you get to what's called a black hole. And so basically what happens with neutron stars is the electrons, because the mass is so great, between 1.4 and 3 times the mass of the sun, the electrons get squeezed into the nucleus and they join with protons to become neutrons. So the entire star is just a whole bunch of neutrons crammed together in a very, very small space. Well, that'll hold up between 1.4 and 3 times the mass of the sun. But suppose an object after the supernova explosion has 3 times the mass of the sun or greater. It turns out that there's nothing at all that can prevent gravity from collapsing this object. And this, of course, is the famous black hole, where not even light can escape these things. They have so much gravity that the escape velocity at the surface of a black hole is greater than the speed of light, or right at the speed of light at the outer edge. Okay, and this actually, the center of a black hole is what we call the singularity. It's actually a tear in the fabric of space and time itself. The laws of physics break down at that point, and we really don't know what happens right there at the center. So that's an ongoing area of research. Okay, so this is just showing you the different things that can happen with the low mass stars. At the end of their life. So this is the interstellar gas cloud, the cloud between the stars that's made up mostly of hydrogen and helium. The protostar forms from the collapse of that, or many protostars actually, and then you get these main sequence stars. The low mass ones go from the red giants to through a variable stage, and then ultimately to red giant, and then become white dwarfs. Some of them will actually, these things around the mass of the sun will actually give off a planetary nebula stage, but ultimately become white dwarfs as well. And then the very high mass, that is 10 times the mass of the sun or greater, will undergo a supernova explosion where the end is not a white dwarf. It's either a neutron star or a black hole, as we just discussed. Okay. So most stars in our galaxy are binary systems. So our star just didn't happen to pick up a partner. Jupiter, some people feel, is basically a failed star. If it needed a little bit more mass, well, not a little bit, a lot more mass for it to become a star. But a lot of the stars in the Milky Way, at least half of them are binary systems. So there's two stars orbiting each other. And there are also star clusters. Many within the disk of the galaxy. There's many thousands upon thousands of stars that exist as clusters. And out in the halo around the galaxy, there's a region where these clusters are called globular clusters, and these are really old, ancient stars. They all orbit the center of the galaxy. Galaxies are collections of stars, so that's which are all gravitationally bound to each other. There are billions upon billions of stars. Like our Milky Way has at least 100 billion stars. Other galaxies have perhaps 500 billion stars, really large galaxies, and then there's some that are maybe have a billion stars, much smaller ones. Galaxies. Surrounding galaxies, there is this region where you find the globular clusters that I mentioned down here, where there is this material called, or this something we don't really know, called dark matter. And so the dark matter is responsible for gravitationally influencing the galaxies, and we see this gravitational influence around all the galaxies that we see. It's not just our galaxy. All the galaxies that we can make measurements on have this dark matter around it. And what the nature of this dark matter is, we really don't know. It is matter is something that is gravitationally interacting with the galaxy, but we can't see it no matter what type of radiation we use, all the different colors of the rainbow, all the different parts of the spectrum that are available to us, gamma rays, X-rays, everything, radio, microwave, all that. None of it bounces off of this stuff. So we really don't know what it is. Galaxies tend to cluster into larger clusters. There's many clusters of galaxies, and then clusters of clusters, which we now call superclusters, can contain billions upon billions of galaxies. Our galaxy, the Milky Way, and Andromeda, we're all part of a much bigger supercluster called the Virgo supercluster, just because that's the direction that this cluster is and is moving. All right, the Milky Way. Okay, so this is again going backwards a little bit. This, of course, is the band of stars. You don't see it like this. This is a time-lapse picture, but this is our Milky Way. It's many stars seen kind of edge on because we're part of the Milky Way. Let's see, it's about 100,000 light years across. It contains many, at least 100 billion stars. This is what it would look like if you were, above the Milky Way somehow and looking down. There are spiral arms that extend from a nucleus. This is what it looks like from the side, and then around the Milky Way, this region is what's called the halo. That's where you find the globular clusters, and of course dark matter. That's where the dark matter exists. As I said, there's other galaxies out there. This is the nearest large one to us, called Andromeda. It's 2.5 million light years away. There are elliptical galaxies which don't have any spiral structure. They kind of look like a football. There are barred spirals where the center is basically kind of a line of material instead of a kind of more of a sphere. And then there are irregular galaxies. There's actually two irregular galaxies in the southern hemisphere, the large and small clouds of Magellan, which are actual galaxies unto themselves, but they're tiny. They actually orbit the Milky Way. All right, so In the Big Bang model of the universe, this is the best theory, right, we have that explains everything that we see, is that the universe itself began as a single point. And there was no space and no time, no matter and no energy outside of that point. Everything that will ever be came from this point of infinite density. We don't know how it gets started, but the moment it starts, space begins to expand. And we have proof of that through what's called the cosmic microwave background radiation. And the universe has been expanding for the last 13.8 billion years, and it's going to continue to do so. And basically what that means is the galaxies are getting further and further apart. It's like imagining, raisins in some bread. As the bread rises, the raisins appear to be getting further and further apart. And they are, because the bread is rising. It's not the actual motion of the raisins, just like it's not the actual motion of the galaxies that we're seeing. It's actually the expansion of space and time. Right now, the evidence shows that the universe doesn't have enough matter. You might think that eventually the expansion might slow down and even stop and reverse itself on some kind of big crunch, kind of going backwards. But there's not enough matter and energy in the universe to stop the expansion. It seems all the evidence right now shows overwhelmingly that the expansion will keep going forever and ever. And not just that. Back in around the year 2000, we found something even more disturbing, is that in the last about 5 billion years, the universe has expanded even more rapidly than it did in the past. It was going nice and linearly, and then about 5 billion years ago, it accelerated its expansion. So it's expanding even faster than it was in the past. And so, it's definitely not going to go back. By the way, we call that the cause of it, which we don't really understand, but we at least came up with a name for it. It's called dark energy. So dark energy is whatever is causing the universe in more recent times, in the last 5 billion years or so, to cause the universe to expand more rapidly. So this is space itself. This is what we're talking about. The distance between objects in the universe is growing as time goes on. And there's nothing anyone can do about that. That is just part of the universe, the way the universe works. All right, and that's it.